Hello and welcome to another video in this introduction to the Digital Power Designer, the add-on to solidThinking Embed. Okay, so what we'll do in this one is we'll look at the tool section. In the tool section, we've got various tools that help in the design of digital power supplies. One, of course, is converting analog coefficients to digital coefficients. What we've got here is the typical compensators, PI, PID, type 2 and type 3 compensators, and we also have some Sallen key second order filters. These are based on, for example, the analog designs so that we can get the resistive and capacitive component values. We can insert those, insert the desired sampling frequency, and we can calculate the digital coefficients directly. So for example, if I put in display here, let's put in some more displays. Might as well do them all for all the coefficients, and we'll sort them out. We can run this, okay, and what we've got here is directly from the analog coefficient, the analog component values here. Now we've now generated the PID gains, the poles and zeros, the S coefficients, and the Z coefficients using the Tustin transform. Okay, so these coefficients can be directly used in digital compensators to control digital power converters. You can export the generated Z coefficients here just by simply putting in the file name, and you can use that later in compensator values in simulation or directly encode general blocks to generate to a microcontroller. Another alternative here is you can enter in the converter value coefficients. First the topology, the gains, the nominal voltages, and the desired gain crossover frequency. And with this here, if we run the simulation again, you can generate the Z coefficients required here. Okay. Obviously, you can enter the values directly, poles and zeros, or the gain coefficients. In this case, as it's a PID coefficient, we can represent it in both ways, either in gains or in poles and zeros. Another feature in this block here is, apart from demonstrating how this is done, we can plot the frequency response. So here we have the frequency response of the compensator in blue in analog terms, and in digital terms is the green. Okay. Then in other tools we have coefficient converters. And with these tools here, what we're doing is in simulation or other methods or other uses, we can put in in a familiar format the poles and zeros of the converter and directly output the gain coefficients. Here we can go into examples, tools, buck converter here. Okay, now we have this here, we can run the simulation. What we're doing here is we can try various coefficient values with the PID converter. This will be directed to the non-familiar digital coefficients to be used in this 2-pole 2Z compensator. We're just outputting these values here into the compensator. These are then running into the voltage mode controller, and this is a soft start which it's doing at the moment. Soft start is being controlled for the first millisecond. And then we have a digital diagram here as we've said in the simulation blocks that are emulating the peripherals inside the C2000 MCUs. Okay, here we have the response if we change some of these, for example, we can increase this significantly, and we should see some sort of stability change in there, unless we've limited this very much. Okay, this one will certainly do something. Okay, because we have a little load, and we can see we've completely lost stability here, so let's wind these down. And we can play around with those. As we've seen, this now is locked out because it's gone into over voltage, and we have this in the control here. These blocks here now are the real blocks which can be used in the simulation. Okay,